Hello, everyone. My name is Alexander Petrescu, and I'm a software engineer on the wearables platform team within Meta Reality Labs. I'm excited to talk to you about bringing AI into the real world, specifically the architecture and design for Meta AI on Ray-Ban Meta. We started on this journey with the belief that for AI to be useful, it needed to be where you were. It needed to see what you see and hear what you hear. We're not alone on this journey. The industry for the last 10 years has also been on this journey. We now have assistants on our computers. We have assistants in our home via smart home devices that you can talk to across the room. We have assistants built into our mobile phone operating systems. And now we're starting to build the next generation of wearables that allows us to bring AI and assistants as close as possible to the user's perceptions. We think that when we give AI these capabilities, it can enable all sorts of useful things that assistants can do for us. For example, remembering where we parked. That's a big problem for me. Just happened recently. I used Meta AI for this particular scenario just a couple of days ago. Hopefully, when I get back home, I can ask it again where I parked and it should be able to tell me. Next, AI can then interact with more complex objects throughout our world. For example, QR codes are a thing that are showing up everywhere from museums to our menus, and we can use AI and assistants to be able to start to interact, to understand this content and be able to interact with it. Next, it can be useful in our day-to-day life. For example, you're walking around your neighborhood, you see a house for sale, you're curious where's the nearest school or how long does it take to get to work from that particular place. You can start to ask assistant things like that when it's where you are. It can see what you see, and it can even interact with things like the sign and call that phone number. But also, AI could be useful for situations that are a little more lighthearted. You're spending time with your kid, you're pushing them on the swing, being able to take a quick video of a particular moment to remember it for later is a very wonderful use for assistants. So I'm going to talk a little bit about some of the challenges to building wearables, specifically the unique ones. We're going to talk about the Meta Ray-Ban architecture that allows us to solve some of these challenges. We're talking about optimizations for Meta AI requests in order to get the most speed and reliability out of them. And then we'll talk a little bit about what's coming soon. So bringing into the real world, bringing devices into the real world isn't easy, as most developers know. However, I'm going to talk a little bit about some of the challenges specifically to AI wearables, challenges that from talking to other people were interesting and were unique and maybe they hadn't thought of. I'm going to talk about 4 different types of challenges: design, hardware, physics, aka the real world, and unique feature requirements that have dependencies on all these, and requirements put constraints on design or physics or other things. They're all really interrelated, and so a change in one can have cascading effects throughout all of them. So thinking first about design, a wearable can't only be functional. You have to take into account people's fashion sense and real world scenarios. In order for it to be accessible where they are, it needs to be worn, right? It needs to be on with the user at all times, or at least whenever the user wants it to be. So that means it needs to be able to be used and wearable in your office, your home, when you're going out with your friends, or when you're on a ski lift. All of these scenarios are real world scenarios, and the design aspects of the devices are really important. For example, my wife has multiple pairs of prescription and sunglasses. And so it was a challenge to get her to use Meta Ray-Ban glasses since they don't necessarily fit her design aesthetic in all of them. However, we're lucky enough to have partnered with EssilorLuxottica to be able to bring many different styles to market with Ray-Ban Meta. And this has helped us solve some of the challenges, such as different head shapes. So we have small and large glasses. So you might have different nose bridges for different types of people. So all of these are really things you need to consider when building wearables. Next, we've figured out the shape, but now we have to miniaturize all of the hardware and put them into that particular shape. It's like 4D Tetris puzzle. It's really challenging because certain components have to be in certain places. Your speakers have to be near your ears. Your microphones have to be positioned in such a way to be able to understand what the user is speaking at most. The camera needs to be in the best place possible for that scenario. So in all of these situations, you have to place these particular components very carefully within the space you have. But also you have to balance things like weight very carefully, because you want to put like heavier components in different parts in order to balance the weight. So for example, in glasses, you don't want your weight on the front of your face, which can cause pressure on your nose. Next, we're going to talk about the physics, aka the real world here. So we're going to talk about power challenges, thermals, and connectivity. So these type of scenarios, these types of issues come up like for all wearable devices, and unfortunately they tend to be the same for every company and everyone building wearable devices. The first thing you have to think about is, in a power standpoint, is your battery size, which determines our weight of our device, and also its battery chemistry, which will determine how much peak power and total power. With those two things combined, you might have a larger total power and maybe less peak power, or something in between. For example, your total power is how many photos you can take, how long the device can be active for. But your peak power is something interesting because it's how many things you can do at the same time. Depending on the battery chemistry and the outside temperatures and other things, we might be able to pull more or less power at a particular point in time. So that means we can do only a few things at the same time. For example, taking a photo and transferring via Wi-Fi might not be possible depending on the power requirements. So the next, and of course, these devices are out in the real world, and so they will be under real world conditions. And as any EV owner knows, when it's cold outside, your battery range is a little bit smaller and you can't go as far. So it's the same thing for our devices. When it's really cold outside and you're on a ski lift or something like that, or it's 0 degrees, it might impact how much power we have for our features. And so we have to be able to communicate and be able to carefully orchestrate our features to be able to still provide them in those environments. Next, closely related to power is heat dissipations and thermals. So we've miniaturized all these components. However, the challenge there is now they're all still generating heat. Whenever you're using any sort of power, you're going to generate some amount of heat. We have to get rid of that heat in a way that's safe and comfortable for users, since they're really, for example, touching our face or maybe touching our wrists. So we have to make sure that we build in things like heat dissipators and be very careful with the type of materials that we use in order to dissipate the heat in an acceptable manner. We also have to be very careful about the power usage, because not only are we drawing power from the battery, but we're generating heat. So we have to be able to, for example, downclock certain components or not run certain components for a long period of time, because they might generate too much heat for us to be able to reliably dissipate it in a safe way. And so, of course, external temperatures come to haunt us again. For example, if you're on the beach and it's very hot, that makes it a challenge for us to dissipate heat quickly. So it might, much like your phone will sometimes tell you that it needs to cool down, our devices as well will need to be able to tell the users when they're too hot to be safely operated. The next set of challenges are around connectivity. In order for AI to be really useful, it needs access to the world's information. So it needs internet connectivity. We need to be able to send images to our servers. We need to be able to process them, be able to receive their responses. So we have this balance again between power, keeps coming up, right? Power is a thing that haunts us every day, and bandwidth. So things like 4G are great, super fast, available all the time or most times, but they're huge power drains on our devices. So for example, most devices won't have an active cellular antenna. We can have access to Wi-Fi, but Wi-Fi is not always available. You're walking around, you're in the woods, you're somewhere else, you don't necessarily have access to Wi-Fi. Even Wi-Fi Direct or other things can take a considerable amount of power, so you can't use them all the time. And lastly, We have BLE, which is great. It's in the name, Bluetooth Low Energy, which is great on power, but also has many constraints in terms of bandwidth and speed, which causes issues for devices that require sending and receiving significant amount of data during AI interactions. And last but not least, we have to deal with what happens when you don't have connectivity at all. So we've all been in scenarios where you're in hiking somewhere and you lose signal, or you're in a basement apartment in New York City, or you're in a crowded place and the connection's not stable. We want to make sure that our devices are still be able to be used and usable in those scenarios. And then the product requirements, start to add on and multiply the issues of all of these things. We know our Meta AI will require us to send a lot of information to our servers about what the user is seeing and what the user is saying and other device contexts. So we have to be able to send a lot of information potentially during an interaction. And we need to be able to also handle certain commands like take a photo and other short commands really, really quickly and super, super reliably. But since we're dealing with all of this information, such as your phone contact, your message content, these photos, we have to make sure that we preserve user privacy wherever we can in order to make the device useful in many scenarios. And lastly, speed and reliability is a feature for these devices. We want to make sure that the devices operate and respond to commands as fast as possible in certain scenarios. For example, you don't want to take a photo to take too long because the moment might be over. And you don't want the reliability of certain commands to not be close to 100%, because then the user can't depend on these actions being taken. So these are like features for us that we need to make sure that we take into account. Okay, so we've talked enough about the challenges. Let's talk about how we've solved some of these issues for Meta Ray-Ban glasses. We use a 4-part architecture. We have our case and glasses. We have the phone, which is connected via Bluetooth and Wi-Fi to our glasses, and it's running the Meta AI app. And then we have our Meta servers, which are connected to our phone via LTE or Wi-Fi. I'll talk about each one. First, our glasses hardware. We have input and output hardware such as cameras and mics and buttons. We also have compute, a microcontroller, and an SoC. We have a 4-hour battery on our frames, which allows us to be able to take photos or walk around and listen to music or take phone calls. And then we also have an extra 36 hours available of charge in the case. So you don't have to go plug into a wall somewhere in order to recharge your glasses. We'll talk a little bit about how the glasses architecture gives us some of our unique capabilities. So the first thing to think about is our microcontroller allows us to respond to a wake word in a power efficient manner. So we can have the wake word running the entire time that the user is wearing it, so we can respond very quickly to users' commands. For example, really quickly to take a photo or to take a video or to call someone. So it's a very important part that the AI is available all the time, whether at your fingertips or via speech. Next, because we want to process some commands offline and really quickly on device, we have compute for our product logic. So this is where the SoC comes into play, and we run our models and we run our logic directly on the frames itself. We also have accelerators for certain use cases where we want more power efficient models, and we can perform certain actions in a much faster way with on-device accelerators. And then we have the connectivity, which allows us to do certain actions like listen to music all the time via Bluetooth or send commands via Bluetooth, but also Wi-Fi for transferring large amounts of data, such as photos and videos. On the phone, we have the Meta AI app, which provides connectivity for Meta AI to our servers. It also provides access to your communication apps, such as your phone, Messenger, and WhatsApp. This allows us to send messages and receive messages, to place calls, all in a safe way. And then It allows us to communicate with our partner apps that are on the phone. For example, you can control Apple Music or Spotify or Audible, and even interact with accessibility applications such as Be My Eyes. And lastly, it allows us to perform more compute expensive operations on media that is just not practical on the frames. We could do this on the frames, but it would take a considerable amount of battery power. And so we prefer to, for example, transfer media and run HDR or image stabilization algorithms on the user's phone. And the big behemoth here is our meta servers, which run our big models, advanced multimodal models that gives us all the capabilities to be able to, everything from chatbot requests like recipes and information about what happened in the world to current news via plugins or current sports scores. And also it gives us extensibility options for agents to do more and more things over time and more complex. For example, mixing multiple things or doing long-running tasks. And then it also provides for personalized user memory. This allows us to remember user preferences or handle things like reminders or other things that the user has asked us to remember for them. So with this 4-part architecture, our on-device compute gives us speed, reliability, and privacy. The Meta AI app allows us to integrate with the different parts of your phone, like applications. It also allows us to do things in a private way, like run expensive operations on your media, and also provides connectivity for Meta AI. And our meta servers, and that's where we get our advanced AI capabilities, and that's where the extensibility story is, and we can add more and more features without taking up more resources from the user's devices. All right, but making it work wasn't enough. We really wanted to make it faster, as fast as possible. I like to say the fastest that we can get it is when the user has started, but the next fastest is when the user has stopped speaking. So let's talk about a scenario here, and then we'll talk about how we were able to optimize these scenarios. An example utterance in this case, for example, might be, what does the sign say in English? So while the user is speaking, you can transcribe that text. Then you might do some understanding on it. At the end, you'll get a final result, like what the set of actions that the user wants to do. For example, in this case, we need to take a photo. We need to run OCR on it. We need to resize it. We know we need to send it to our server to be able to process. And then our server needs to respond. So the part we'd like to optimize is the user perceived latency in these scenarios. This is the time from the user stopped speaking to the time that Meta AI has responded. So there's multiple ways to reduce this perceived latency, right? We can make each of these boxes smaller. We can make our NLU faster. We can make OCR faster, resizing. But at some point, all of these are expensive and they take time to run, especially with constrained hardware. So we've developed a few other techniques in order to be able to get speed improvements without necessarily making everything much, much faster. The first one is predictive processing. So we can start to understand and analyze what a user says before they're done saying it. We know from user patterns and behaviors that we can probably predict certain actions and certain information that we need to do before the user has finished their complete thought. So once we can do that, we can start using more of our hardware when applicable to be able to run multiple things at the same time. For example, while we're transcribing the user speech, we can start taking a photo or we can do other tasks in the background. Then we can choose to run different models via accelerators ahead of time. This oftentimes means loading particular models into accelerators. So we might load our NLU model or we might load an OCR model into an accelerator to be able to, when it needs to be used, it's there for our application. So let's talk a little bit the same thing, but with optimizations. So the user says again, what does the sign say in English? And so, but now instead of waiting till the very end, we can start to understanding while the user is speaking. We can start to predict these speculative operations like taking a photo, resizing. We can run OCR on an advanced accelerator. And then, we can send it to the server at the end. We do have to wait till the end because the user might change their mind. They might say cancel or they might say something else. So we do have to wait till the end before we actually send to the server, especially to preserve users' privacy, for example. But as you can see in this example, we managed to reduce the user perceived latency while not necessarily making anything significantly faster. All the blocks are about the same size. Honestly, in most cases, a lot of these operations might be a little bit slower since they're competing with resources on the same device. But as long as the overall user perceived latency has been reduced, then that's all that matters to us. So with these techniques, we've been able to make our on-device commands, such as take a photo, take less than 1 second. They're lightning fast. Basically, as soon as you're done speaking, it's already taken a photo. And we're also able to provide these kind of commands with really high reliability, which makes them useful in all scenarios, and you can rely on them. And then even for advanced AI responses, which require multiple hops through the phone and through our servers, sending media and dealing with all sorts of network connectivity, we can still respond on average in under 3 seconds. Let's talk a little bit about what's coming soon. So agents, that's what we're all here for. Those are going to provide much more capabilities for our users, but they will come with their own challenges in terms of reliability and speed and performance. So those are exciting, but they also have their own challenges. We're going to bringing a Meta AI on Ray-Ban Meta to more markets. For example, we just launched in India and Mexico. And then we're going to bring more features such as live translations, which allows you to speak with another person in a different language in real time, even offline. So, of course, that'll bring even more challenges in terms of power utilization. We have more competing workloads, and we have more potential for model misses as we move to different markets, and people can say the same, can want to say the same things in different ways. And so it really takes a village to build something like this. We have a lot more work to do in order to optimize our different scenarios and handle all these new challenges. But it really takes everyone here in order to be able to solve and make Meta AI for Ray-Ban Meta a reality. Thank you.